All right, so I want to first recap um, what we've kind of learned. So we've talked about, so this will be DC motors will be the third type of rotating machine, and the last type of rotating machine that I'll talk about. Okay. The first two that we did were the synchronous machine and the induction machine, which are both AC machines. Okay. The term AC versus DC basically refers to, what's the voltage type that you apply to the terminals when you're using it as a motor. All right, so for a synchronous machine, I apply a three-phase AC, and I apply a three-phase AC for an induction machine. I specifically say three-phase because there really is not such a thing as a single-phase induction machine or synchronous machine. Just as a test, why would there not be a single-phase machine? You may not fully remember this, but what was special about three-phase? They make the fields rotate. If I just had a single phase, the fields were stationary, and that basically there's no such thing as a single phase machine as a result. Now I can't have a two-phase machine. That will work. And so if you've ever fixed an air conditioner or whatever, you know that there's a capacitor in there, and the capacitor basically what it does is it creates a 90-degree shift to another voltage, so that there's a two-phase machine when you start it. Okay. You can let a single phase machine run, but it can't start. All right. So that's single phase motors are the world's crappiest sort of motors. None of you are ever going to design one. And most likely in your lifetime, they'll disappear because they're inefficient. So I don't really focus on them too much. All right. Three-phase induction machines are important to understand. All right. But so I don't really focus on single phase for that reason. All right, but if you've dealt with them, you may have dealt with them, right? So your air conditioner has one, right? And so they're important to know that they exist, but they don't function in and of themselves. Okay. All right. Synchronous machine versus induction machine. Synchronous machine, this is our two-pole machine. Put a DC current in the field coil, three-phase voltages on the stator coils. The key thing with this guy, for him to produce torque, what had to be true about that field that was created by the stator and the rotor speed? They have to be synchronized to each other. And the power production for this guy, the power production, which is related to the torque production, right, is to say this guy is 3 times the magnitude of the voltage times whatever that voltage internal to this thing is, over XD times the sine of delta. So the important thing here is this is true if the two things are operating in synchronism with each other. In other words, the field and the rotor, if they're operating in synchronism, this is our power relationship. What is delta? Power angle, right? So power factor is just the current and voltage angle. So basically the angle between the current and voltage. This delta here is basically related to the angle between what and what. Yeah, so yeah, VA, specifically delta is equal to the difference between the angle VA and the angle of EAF. And at a fundamental fields level, this is also related to the angle between the two rotating fields, the one coming from the rotor coil and the one coming from the stator coils. All right. So basically the rotor moves itself, shifts itself over time, to make sure that it's providing the exact right amount of power. All right. So we basically said, hey, if I increase the power going into the machine, the speed, the angle delta changes itself over time to make sure that I provide just the right amount of power that is needed to go onto the grid if this thing's a generator. All right. So what we saw is if I increase the power, the mechanical power going into this thing, we saw that the speed, at least on a transient basis, increased itself or decreased itself, but always went back to the synchronous value. And it was doing so as delta ultimately changed. So delta would go through a change. All right. So that angle is important with this guy. What's it mean to say that it's two poles? Yeah, the field basically changes one time as they go around. So it points into the rotor and then out of the rotor, right? And if I had a 4-pole, it would go in, out, in, out. So it would have basically, it would be like I had so 2 magnets. All right. So to say I have a 2-pole field means it's like I have 1 magnet, right? A north pole and a south pole. All right. This is our induction machine. All right. Got a 2-pole version of this. You almost never see a 2-pole induction. Not almost never. The most common probably is a 4-pole. All right. You'll see 2-pole, but most common is probably a 4-pole. Looking at this, these are the critical elements. I've got my single phase circuit model. This is 1 phase of the circuit. Basically, we said this guy operates like a transformer, right? What I do is I put a set of voltages on the primary windings, which is basically the stator windings, put a set of voltages on there, and what happens on the rotor? What's that? Induces a current. Yeah, induces a voltage or induces a current. Usually, in this case, I'll say it induces a voltage because usually they're short-circuited windings on the rotor. Okay. And this model looks a lot like the transformer model. What I've done is I've taken the impedances on the secondary, which in this case is rotating, and I've reflected those impedances over to the primary. Okay. The thing that's weird about this guy is what I have this resistance here that's proportional to a speed, the mechanical speed of the machine, right? I said if this guy gets all the way up to full speed, okay, what's true about the current in the rotor, right? In other words, if the rotor is running at full speed, and its full speed is related to the speed of the grid, at full speed, is there any current in the rotor? No. Right? If he slows down a little bit, then there's a current induced that's basically related to the difference between the 2 speeds, the difference between the speed of the field and the speed of the machine. All right. So that leads to sort of a summary of a couple of different important terms, all right, for this guy. Basically, the electrical frequency omega. All right. This guy here is the frequency of the currents and voltages that I apply. And this is, our typical 2 pi 60. Okay, for omega. Now there is the mechanical speed, which I always write omega m. That's the speed that the motor is moving at. Okay, that is typically going to be just a little bit less than what I call it the synchronous speed. Okay, the synchronous speed, that is the fastest speed the machine can go. All right, we're going to go through an example of this, real quick. But basically, if I had a 2-pole machine, all right, the maximum mechanical speed that thing could ever go would be 3,600 RPM, or that 3,600 RPM is 60 hertz, or 377 radians per second, right? All 3 of those are equivalent units. If I had a 4-pole machine, the maximum it could ever go is 1,800 RPM, or 30 hertz, or 377 divided by 2, whatever that is. Okay. All right. The frequency of the current in the rotor is not usually all that important to us. This omega minus P over 2 times omega m. If I'm looking carefully at those numbers, that's going to be usually a really low frequency, right? We looked at an example of that last week. The key thing to us is the slip value here. All right. Slip is what I have in the circuit model, right? That resistance depends on slip. If I look at this just intuitively, and we're going to calculate an example here in a second, what is this? I mean, what it is a per unit value, right? But it's basically telling me as a fraction how far off the mechanical speed of the rotor is from its full speed. All right, that's basically what it's telling us. And typically, we looked at these are our key performance metrics. We usually look at what we call a torque speed curve for this thing. So this is a classic torque speed curve, and it's done in per unit, both per unit. So there's per unit torque there on the left side, and then per unit current on the right side. All right. And that's a typical way of specifying that, because this is independent now of the machine rating. Okay. What this says is that at my operating point, so in this particular case, if I'm operating, let's say right here, what's special about this point is what I'm showing is this curve here. This is the torque electrical. This here is the torque mechanical. And at the operating point, those two things are equal to each other. All right. At that particular point, that torque is exactly, so those two are exactly balancing each other. And I'll notice that as a percent of synchronous speed, which is the maximum speed this guy can go, he's operating usually just a couple of percent lower than that. All right. If you look at a typical motor nameplate, you're going to see numbers like 1780 RPMs, kind of the rated value. So just below that sort of synchronous speed. And one thing we said too, if I look at the current here, as the motor gets slower and slower, the current drawn by the motor gets higher and higher and higher. All right. That leads to something we call an inrush current, which is to say that when I start the motor and connect it, there's a very high current that it's quote unquote inrushing into the motor to get it started. That high current's a good thing because it helps this thing to accelerate, all right, faster. You'll notice here, not to say there's no hard and fast value on that, but you'll notice what this says is that at 0 speed, the current is on the order of about 600% of rated. In other words, it's about 6 times higher than what its rated value is. That's about right. There's no hard and fast number on that, but most motors that I've ever seen, usually on the order of 6 to 8 times higher at starting. All right. And that's, so if you go into the world of protection or something like that at SEL, one of those kinds of companies, right? Motor protection, that's one of the things you typically worry about is if the motor stalls, in other words, if it can't turn the pump or the compressor or whatever it's supposed to turn, you have to trip breakers and stuff, because basically you're going to be stuck at this, what we call locked rotor current at starting. All right. So anyway, let's look at an example on that one. So this is the same machine I looked at last week. Let's say what I have is this guy is rated. I'm applying the rated voltage, 2300 volts line to line. Okay. I got all those parameters right there, and he's operating at 1773 RPM. All right. So let's say that's where he's actually operating. So there's some load on it, and that's where he is. And what I want to do is I want to go through and I want to figure out, well, what's the torque that this guy's making? What's the air gap power? What's the mechanical power? What's the input power? And what's what I call the efficiency of the machine? Okay. So first of all, let's take a second to think about the efficiency. So this is, rather than just making Greek stuff here, let me, this guy is efficiency. I'm gonna give myself more space to write the word efficiency. So what do you think the efficiency of the machine is? Power out over power in. Yeah, that's right. So what that is the mechanical power divided by the input power. So what that comes down to in the context of this circuit is the input power is going into the electrical terminals. The mechanical power is going into the shaft. That is not the power going into this resistance. The power going into this resistance, just in summary, the air gap power is this. That's the power that is transferred across the air gap. In other words, basically transferred to the secondary of this transformer. Okay. This guy consists of what I call the rotor power plus whatever mechanical power is transferred. All right. The rotor power is just the losses in the windings on the rotor. Okay. This guy would just be 3 times I2 squared R2 like that. All right. How much is being lost in heat? Okay. This guy has a couple of places where heat's lost, right? One of them is this winding resistance on the secondary, sorry, on the primary, on the stator. And the other one is windings inside the rotor. Now in problem 3, I think it is, or 2, problem 2 on the homework, I also give you mechanical losses, right? So there is another source of losses, right? This guy, and let me just shift over real quick to this picture. So this is, I wanted to show you guys what an actual rotor looks like. I brought in the stator before, the induction machine, but just to be clear, all right, this is a rotor on I think I want to say it's 1.5 horsepower, maybe a 2 horsepower motor. All right, so what you can see here, if you look carefully, you can see laminations of iron. It's got sheets of iron for the rotor. And then what you see here, these bars is aluminum. All right, and if I look through, I'm not sure how well you guys are gonna be able to see it. I can see it pretty well from here. I'm not sure how well you guys can see it there. Along the side there, you see there's like silver pieces kind of broken in there. What that is that's the cage, right? So this is a squirrel cage motor. What they do when they actually build this is they pour molten aluminum down into a bunch of gaps. All right, so there's basically aluminum bars running through this thing. On a bigger machine, this would be copper. All right, but on a small motor, it's usually aluminum. All right, so you can see that this is short-circuited windings. There's holes inside here, but basically there is no electrical connection, right? Basically, there's these short circuits at the two ends of it. Okay. All right, now to say that there's friction comes from like when this guy's spinning, comes from a couple of different things, right? So one is I've got a set of bearings here, ball bearings, right? So there's friction that comes in that. There's friction that just comes from the fact that when this guy's rotating, air is basically hitting this thing. So there's friction in the air and stuff like that. In the example I have here, I'm not considering those losses, but in the problem I give you in the homework, I do consider those losses. I think it says it's like 400 watts of loss in that particular case. Right. All right. So that's what that looks like. It's important to kind of have that in your mind. This is what a squirrel cage rotor would look like. Right. All right, so let me go back to this example then. All right, so what I want to do is I want to get to calculating all of those things. So for me to do this, what do I have to calculate? If I want to get to the torque, nope, I need to switch back. For me to get to the torque, what do I need to calculate? There's power. I have to go to the circuit model. I've started doing some calculations from the circuit model. In other words, specifically, if I go back and look at my torque relationship, right, I have to get to an understanding of what I2 is. In other words, what's the current in that secondary winding on the rotor side? Other thing I have to figure out is not just I2, but I have to figure out what other thing. Well, I'm going to need IAS to get to I2, right? So I got to do circuit analysis. But to even do the circuit analysis, I need to know the slip. All right, I need to know what that slip value is, which means I got to start looking at the speed stuff first. Okay. All right. So first of all, just to be clear too, 2300 volts line to line. So if I'm going to do my calculations, I want to figure out what VAS is, right? So VAS is my stator side line to neutral voltage. So what is that going to be as a phasor if I have 2300 volts line to line? 2300 divided by square root of 3 with an angle of 0 degrees. The angle is not particularly important, right? I can just shift the current to accommodate it, but usually we just say that A phase voltage is 0 degrees. Okay. All right. So we're going to do the analysis with that. So I got to start by looking at the slip, figuring out what the slip is. Okay. And I didn't say how many poles this was, I probably should, but based on what I've said so far, how many poles do you think this thing has? 4, right? So P is equal to 4. All right. And if I hook this thing up to a grid that is 60 hertz, all right, which I unless I'm in another part of the world, I'm usually on a 60 hertz grid. All right. That means that my omega, my electrical frequency is 2 pi 60 or 377 rads per second. Okay. So what I want to do is I want to go through and figure out all those other speeds. I defined a whole bunch of speeds here. All right. What am I giving you? Which speed am I giving you with the 1773 RPM? Not omega S, but omega M. It's the mechanical speed. Omega S is the maximum speed he could ever go. That's what I call the synchronous speed. Okay. So omega M here is 1773 RPM. So revolutions per minute. And again, all my SI stuff assumes this stuff is in radians per second. So I got to convert that to radians per second. So how do I convert this to radians per second? Totally. Yep. 2 pi over 60. And I come up with a number. I don't really care what it is, but I think I wrote it down. Yeah, it's 185 right down below. 185.6681 rads per second. Yeah, the other thing that's important to me is what's the synchronous speed. Now, the synchronous speed, again, is the maximum speed this guy can go. If I go back to my definitions over here, right? It's related to the field speed, the way that the field is rotating. So it's defined as omega divided by p over 2, right? So basically by the number of poles, right? If I do the math on this, this works out to be either, if I do it in radians per second, 1.88.4956 rads per second. Again, no real engineer would ever say that. They would say it's 1800 RPM. All right, is the speed on that. All right, so with all that information, I can calculate the slip. All right, now the slip, there's an equation for it. But again, what is it? It's a fraction of how far off my actual speed is from the synchronous speed, the maximum possible. So it's basically the synchronous minus omega M divided by omega S. So in other words, if you intuitively, this should make some sense. If I'm operating at full speed, okay, I'm already full speed is synchronous speed. What's slip going to be? If slip is if I'm at full speed, so omega M is equal to omega S, the slip is going to be what? 0, right? There's no slip. In other words, the field and the rotor are at the same speed. Based on what I have right here, if I plug in those numbers, what I work out to is, oh boy, I didn't write it down. I think it's about 1.5%. Let me see. I think that's what it works out to be. Yeah, 0.015, so 1.5%. Okay. All right, so let me go back. Yep. 0.015. All right, or the other way that's sometimes written is 1.5%. All right, that's 1.5% off from his maximum speed. Okay. For some reason too, this is one of those questions, like on an FE test, they like to ask these questions about motors. So that's usually about as challenging as it gets, I think, for motors on those FE tests. But this is a common one that you might want to bear in mind, where they ask about different pole speeds and stuff like that. Okay. All right. All right. Well, so then now that I have that, what do I do? How would I get to my I2? Circuit analysis. Yeah. So I got my VAS, right? So this is where I'm applying in particular, if I do this in the phasor domain, right? So in my pictures here, I'm writing these when I do the little v, little I, long story short, that's standard notation for what I do when I'm talking about time domain variables. When I do those capital V's like that, capital letters, that's what I do for phasor stuff. Okay. So what I do is I go through and I do my calculations on this guy. I want to figure out what I2 is, but getting IAS is a lot easier, right? So IAS should be, right, just simply VAS divided by Z, right? And then this is where Z is the total impedance of that whole thing. All right. And then said if I wanted to get to I2, what's the easiest way to get to I2? Do a current divider is the simplest way to get to it, right? I'm not going to go through all that. You should be able to figure out how to get to that. But if in doing it like this, a couple of things that I did, I plugged in that S equals 0.015, and I get that R2 over S. I find that easiest to do. I basically define that as a variable. It makes the math a little bit cleaner when I'm trying to track all those variables in MATLAB. This guy works out to be about 12.4667 ohms. And if I do my math on this, IAS ends up being 99.4481 amps with an angle. Let me ask this. Where's that angle going to be? Without knowing what the angle is, where's that angle going to be? Is it fourth quadrant or the first quadrant? Fourth quadrant. Why fourth? It's an inductive load, so it's going to be, it better be a lagging load, right? So this guy's going to, and it works out to be negative 16.2735 degrees. And when he's operating, typically, you can look at the nameplate on the motor, but typically it operates at a power factor of 85% or higher once it's operating. If it's unloaded, let me ask you this. If the machine is unloaded, no load connected to it, in other words, no pump or anything like that, it's going to speed up. And unloaded, what speed should it operate at in theory? What's that? Synchronous speed, right? So at synchronous speed, the slip is 0. So what's true about this R2 over S? It's infinite, right? So in other words, there shouldn't be any current over here in that condition, right? In that particular case, at synchronous speed, no load, the Q value is going to be relatively high. All right, where the power factor will be relatively low because all the current will be going through this path. And X sub M, the magnetizing reactance is usually pretty high. Okay. So anyway, that's just an important kind of note to make. But when we load the thing up, usually it's at a pretty high power factor. Okay. All right. We got that value. If I get I2, all right, my I2 value works out to be, and I don't care. In fact, I didn't calculate what is I2 as a phasor, right? Because if I look at my formulas here, I really just need to know the magnitude of I2. All right. And to be clear, could I ever even measure I2? I couldn't, right? I'm showing you what the stator looks, or what the rotor looks like. You're not slipping a current transformer. There's no way to measure that current on that thing, right? The only thing I can do is measure it from the terminals on the stator side, right? And I can relate it to what's going on the rotor side. I'm never going to be able to measure it directly. So I get what its magnitude is, right? Its magnitude, let me ask you this. Will its magnitude be smaller than 99.481 or bigger? Smaller. Better be smaller, right? Because I got a current divider here. So it better be a smaller current. There better be more current going into the stator than there is going to the rotor. Always, that's a good sanity check to perform, right? This guy works out to be about 94.888 amps. All right. Again, hopefully this should make a little bit of sense. It says the majority of the current that's going into the stator is going where? To the secondary, where it's doing useful work, right? The current that crosses that air gap is making torque, right? The current going through here, right? Some of it, this says about 5 amps is going through XM, and that current going through XM, what's its job? Basically to create the magnetic field. That's all it's doing. All right, that's where the Q is coming from. All right, the useful stuff is basically going into work over here. Okay. All right. So, and then at that point, I just got to go through my formulas here to say, okay, well, what's the torque in the and then what's the power and all that good stuff, right? So I basically put it through my equations to get all that stuff, and it's not that hard to do it. It's pretty straightforward. If I do that, okay, what I end up with is that the power mechanical, right? That's the actual power going into the load, right? The power mechanical, which would be omega m times the torque, right? That works out to be, in this particular case, 331.69 kW, which again, we typically put in horsepower, all right? But saying I got about 331.69 kilowatts going in, or sorry, coming out, all right? Now, what should be true about the input power? Should it be bigger than that or smaller than that? Better be bigger, right? Because there has to be some losses. Better be, first of all, better be at least the same amount. I better be putting in 331 if I'm getting 331 out, all right? The rest is basically going to losses. So how do I calculate the input power? What would be the way to do that? What's that? Yeah, that's right. Yeah, so basically, if I talk about the power here, so I still have my usual relationship to say that the complex power is basically P plus JQ, right? Where this would be P in, this would be Q in, and that's got to be equal to 3 times V, well, right, yeah, 3 times VAS IAS conjugate, like that, right? My usual way of writing out the power as if it's just a three-phase circuit, because that's what it is a three-phase circuit. Okay. And if I do that, I didn't write out what the Q is, but I know that the P is the real part of this, right? So if I take the real part of this whole thing, I'll get the P. And the P that I work out to, P in is 344.5 kW. So my efficiency, which is the mechanical output power divided by the input power electrically going into this thing, works out to be 0.9628. All right, that says this guy is 96% efficient. A little bit higher probably, because I haven't included the friction losses and stuff like that. But I would expect, I don't know off the top of my hand. This is a 500 horsepower machine. What they call a NEMA. So NEMA is the agency that rates motors, right? For a NEMA premium efficiency motor, which is what most people would buy nowadays, it's probably about 96-95% for a 500 horsepower machine. All right, machines that have lower than a 90% 90% efficiency, those are the ones you find in your air conditioner or whatever, right? They're they're grade Q motors. Because it only takes so the motor, yeah, good question. The motor, the fan motor, let's say in your air conditioner, is probably 1/6 horsepower, right? I mean, I don't feel uncomfortable grabbing the shaft of that thing and not having it hurt me. It's just a weenie motor. So at low power levels, it's just not worth it for the cost to make an efficient motor, right? That's really what it comes down to. Now, nowadays, as we get more and more kind of Energy Star appliances and stuff like that, then yeah, you're starting to see higher efficiencies, but still your run-of-the-mill stuff is not like that. At 500 horsepower, you're going to make it more efficient. It probably also runs 24/7 and once I get into those larger motors usually. All right. Questions about this? This is very similar to what you have in problem 2. The only difference in problem 2 is, like I said, you have that. I ask you about the shaft power, which is the actual power going to the shaft, so to the loads. When I say the shaft, what am I referring to? Is I am saying to the shaft, basically here, right? That is to say that the mechanical power is basically everything going into rotation. So it would be, the friction in the bearings and the friction from what we call windage as this guy spins. The shaft power is what's actually getting transferred to whatever pump or fan is connected to this thing. All right, so there's a little bit losses that I'm not adding in here. Okay. questions on that? Okay. All right. So there's a lot you can say about induction motors and how you design them and all that kind of stuff, but this class is not really getting into design, and I just want to make sure you guys get the basics. All right. So what I want to do is I want to shift over to DC motors. All right. So DC motor is, like I said, really, really simple sort of device. All right. And it basically operates again off my simple basic principle of the Lorentz force law. All right. Which is to say, if I have this set up, there's going to be a current that goes out of this battery through this wire. So there's going to be current I is going to be going that way. Which direction is and I'm using magnets because usually in the case, I always use this picture, I guess, but usually in the case of DC motor, the most common ones, probably all the ones that you've ever used, and chances are probably a lot of the computer engineers, if there's any in here, have used DC motors for, Conrad robots and things like that, right? When you do that, typically they have magnets inside of them. All right. And the one I'm going to show you here does. So I've got a North Pole and a South Pole. Where's the magnetic field? From north to south. So there'd be a magnetic field shooting across here, B like that. And the force is, we've said this before, IL cross B. Right? So which direction is the force? So I cross B, it's going to be up, right? This wire would jump up, right? That's the basic premise that we're going to use inside of the DC machine, all right? And this is what a DC machine looks like in sort of an exploded view. And there are several different ways to make this thing. I've done it in the most general way, which is to say I've got two sets of windings. One of them here, this guy is what I call a field winding. Just like we had a field winding in the synchronous machine, its job is simply to create a field, right? I could create a field different ways. One way to create a field would be magnets, okay? Like I just showed in that picture, right? So the job of the field winding in the context of this picture, the job of the field winding would be to create this field that goes from north to south, all right? That's the same thing that's going on in the synchronous machine too. There's a field winding, right, that is creating a field, and then I'm putting some currents into that field, okay? All right, so in this particular case, what I have is, the other thing that we refer to here is the armature. And these are a lot of old school terms that people use, but the armature, sometimes people also refer to those stator windings on the induction machine and the synchronous machine as the armature windings. All right. I'm going to use I sub A typically for what I refer to in the DC machine. Okay. Now, the thing about the DC machine, all right, which I've got a wee little itty bitty baby one here that we're going to take a look at. The thing about it is the currents on this guy are on the rotor. All right. I put currents onto the rotor. And that's the same thing that I said I was doing in the synchronous machine. Somehow in the synchronous machine, I had a way to get currents onto the rotor. And the way I do that, let's take a look at this picture here. So I'm going to go to the dot cam for a second. All right. Now, again, I said that guy's a wee little bitty guy, and he is. This is the rotor here. This is the stationary piece. Now and again, this is a pretty common sort of thing like you might have in a robotic sort of motor, right? Where what I have here, if you look, you see this blue piece and the white piece. You want to come up and take a look at that later. Basically, one of those is a north magnet, one of those is a south magnet. All right, so this guy is a permanent magnet type motor. So there's a field here, and I take this rotor, and you'll feel it. And as I take my, I don't know what you guys can see this, but you can see as I move it close, it's basically getting pulled to the two sides because they're magnetic. These guys here are iron sheets again. And I see I've got all this sort of orange stuff here. What's all the orange stuff? Windings. That's my copper, right? So basically I got windings all around this guy. Those are the windings that I have on that station, on this rotor, okay? So here, I have all these windings on the rotor. Now, there's a very special way that this guy is wound. But the other important thing about this is this, so see, I've got one side of this thing still here, right? I took the other side off to get the rotor out. And if I look carefully, I'm not sure how well you guys can see this. If you see here, there's two pieces of copper coming in, and there's stuff at the tips of the copper, right? What happens when this guy is actually operating is there's a copper sheet right here, and the windings are connected to that copper sheet. What happens is he when he operates, he's sitting there like this. So that what's going on is that those copper sheets are touching to this piece right here. That thing is called a commutator, right? And what's going on is I am basically, this is where I sub A gets these tabs, or where I sub A goes in. And then over here, these two pieces are how I actually connect to the rotor coils, okay? In reality, this thing functions like a mechanical version of a rectifier, right? I don't want to get too into that, but basically call this guy a commutator. What he does is he's basically taking DC current and he's feeding that DC current into these windings, okay? So that's the basic picture of what it looks like. If you want to see it some more, you can come up. I'm happy to let you take a look at it. But basically, those the pieces that I just showed right there. So actually, show together, right? These pieces here on this, so there's these two copper strips, and attached to those copper strips, you can kind of see something a little bit bulky on the ends. That's made of a carbon material, graphite type of material, and it's called a brush, right? This is what I call a brushed DC motor, because there is it's like I have a brush touching this thing as it rotates, right? So what I have in this picture here, right, is these guys are the brushes, right? And there's a set of copper strips that are on the shaft that basically direct the current from the stationary world onto this rotating thing. Now, what's special about these windings is basically this guy ultimately, I think he's, and we'll go through the analysis here. So let's see, it's going to be I cross B. Yeah, this machine is going to rotate in a clockwise direction, right, eventually. As this guy rotates, the interesting thing is because of the way the brushes are connected, current is always going to be coming out at you on the top and going in on the bottom. All right, so that's what the dots mean. The dots mean right coming out, the X's mean, so from your perspective, the dots are coming out and the X's are coming in, right? As this guy turns, basically this winding moves to here. And because of the connections, when this winding moves from here to here, what happens is the current reverses direction in that winding. But from a geometric perspective, the currents are always coming out on the top and going in on the bottom. All right. And which windings specifically are on top and which ones are on the bottom just changes as it moves. That means there is a brief period of time when there is no current going in, right? That has to be the case. If you look carefully at this, it's tricky to see that. In fact, it would be probably almost impossible for you guys to see that, but there are, on the copper strips on here, there's little breaks so that it can make that jump as it goes around. Okay. All right. So if I want to understand how this thing works, it is pretty simple. We're not going to get too weedsy on the math with this thing. I want to understand it again from a circuit operations perspective. How should I figure out the way this guy's going to work? Right? Well, we said IL cross B is our basic way of figuring out how any machine's going to work. So looking at this picture, right? If I put, let's say, a voltage source, or ideally I try to put a current source on this thing. Right? If I put a current source on this thing, there's going to be a B field. I've already drawn the direction it's going to go. Right? So when I get to, and again, that B field better be going, B fields have to be closed. So the B field's going to go around the iron, cross the air gap, right? So it's going to go up and around, cross the air gap, go through here, cross the air gap again, and go back around, right? Now, in this particular setup, if I were to draw what the B field looks like in the air gap, what would it look like? So he should, this is a really exploded view, right? If I look at my air gap's typically really, really tiny, we said, right? You can look at it here, right? If I plug this guy in, right, to this here, right? If I put this in here, you can get a sense of what the air gap is. Kind of hard to do it because of the magnets, right? You don't even notice that there's a gap. All right. So my picture is pretty darn exaggerated. That's usually the case. The gap is small, always. All right. If I look at this, my B field should be jumping straight across. Right? For those of you that are really into electromagnetics, you can figure out that it's going to be perpendicular to both surfaces using the boundary conditions from Maxwell's equations. Okay, it's going to jump straight across like that. So if I want to figure out what's going to happen, I can just simply do what? Well, I can do my analysis using the Lorentz force law, right? So I have a current, let's say the rotor has a length L. So L is the length of the rotor. Let's say R is the radius of the rotor. And let's say that there's a B field that exists in this particular case. How would I figure out what the B field is? This B right here. I could do my magnetic circuit analysis if I wanted to, right? But I know that it's always going to be some constant. I'm going to write it as G times I sub F. Right? That should make sense. What's G going to be? I don't know. It's related to mu, and it's related to the number of turns, and it's related to the air gap and all that stuff, right? Somehow I can get it from the reluctance analysis, but I don't want to right now, right? Basically, that B is proportional to the field current. More field current, more B, less field current, less B. Okay. All right. How would I figure out now with this information, if I have a current I sub A into that rotor, what would be the force on any of those windings? How would I figure out the force, let's say, on this winding right here at the top? So the important thing is this current I sub A. So when I hook this guy up on the armature, I hook it up to a voltage source typically. All right. And so a current starts to flow into that machine. All right. So any one of these windings has a current I sub A. So if I'm looking at this top winding, let's say this guy right here, let's get all those lines out of the way, right? So let's say right here, hitting that guy is that B field, and I have a current coming out of him. So if I'll figure out the force, the magnitude of the force on that guy, what would be the magnitude of the force on that winding right there? So it's IL cross B, right, is my force. What's the cool thing about L cross B here? It's 90 degrees. They're normal to each other, right? B is coming straight down. I is going out. They're 90 degrees to each other. All right. That's because of the boundary conditions and everything. The B field and the current are always going to be 90 degrees separated from each other. That means the magnitude is just I, L, B. All right. And specifically, it's IA. Like that. You guys follow that? All right. Now, what direction is this guy going to go? How do I figure that out? So if I look at the one on the top, right, I is coming out, B is going down. So my thumb is going that direction. That means that if I look at this particular winding, there's a force on him in that direction. And if I looked at the one next to him, so it'd be, so for this guy here, it would be in the positive X direction, I guess. Because the B field's going down, right? I is coming out, right? So I get I cross B, my thumb's going that direction. That's the force. And if basically the same result happens for all of them, right? The force ends up being tangential, right? So really it's in the, if I'm being careful about this, it's in the, I don't know, what's that, the phi direction, all right? In a polar coordinate or cylindrical coordinate system, right? So the force on each one of those guys is tangential to it, but they're all operating in such a way that it's going to be pushed in essentially a clockwise direction. Now, if I want to talk about the torque, that's what I usually care about in a rotational system, right? I got to do two things. This was the force on one of them. I can talk about the total force, right? The total force would be to sum up over all the windings. So if I have n windings, the total force is going to be, so F total is basically N times IALB, like that. If I want to talk about the torque, how do I get from, again, that's a magnitude. How do I get from a force to a torque? Yeah, multiply by the moment arm here. And again, I see they're 90, it's really a cross product, but they're 90 degrees separated from each other. So basically torque becomes, or the magnitude of torque specifically, is F total times R, the radius. So it becomes N L B R I A, like that. Okay. Now I moved the IA around, right? I did that on purpose because when I look at this here, N, L, B, and RA, with the caveat that B is some constant times IF, maybe. What's true about these things when I'm operating the machine? They don't change, they're constant. All right. Now, IF could change, so B could change. You don't change the radius while you're operating. You don't change the length while you're operating. You don't change the number of turns while you're operating. All right. If I look at the motor I had right here, right? Am I ever changing the B field on this guy? No, he's got magnets, right? So I can't change anything about the B field on this guy. I did it in a very general sense, where you have two types of machines in the world, right? Those that have field windings and those that have magnets. Either way, they have a field, right? One of them comes from permanent magnets, the other one comes from an electromagnet, right? Where I put a current into the winding. All right. For most of your small, what I call servo motors, things that would be used in, you know, sort of simple household devices or your little Conrad robots or whatever, these things are typically made with magnets for the field. Okay. So from that perspective, I usually think of that B field there, that B value would be in a constant. Okay. Now, questions about that stuff, right? Important thing that I got here is I said, again, if I see you on the street in 10 years and I try to figure out what I taught you, if anything, this is one of the two things that I would expect you to remember. Not that formula, but it's to say that torque is proportional to what? Current. Torque is proportional to current. And that's true in all the motors we've seen. If I want more torque, I need more current. All right. And just to prove that, I have that same motor. Again, this is an important concept to me. Because one thing I know about all of you in this room probably is that you can't think about current, right? I know that's the case. People can think about voltage a lot, right? If I ask you how much power, this is classic, I ask you guys, like, you guys come to me with a senior design question, you're like, I say, how much power do you need? You'll say 10 volts, right? You don't, that's not power, right? The amps part's harder to think about. And it's important because when somebody says, hey, I need a motor to do X, Y, Z, usually you care about how many amps you need because it tells me how much torque I'm going to get. All right, so I need to know that. So if I take this is that same little motor, all right? And I've hooked him up right now to 0.6 volts. So he's operating at a pretty low speed. You can kind of hear him moving. The sound that you're hearing, if you can hear it, and I'll turn up the voltage here. am overdriving this thing. He doesn't like, this guy's meant for like half a volt. So he's kind of screaming. What's the screaming? Well, it's part of it could be the flux is high, right? So it could be the iron making some noise. But that main noise is the friction of the brushes, right? So one thing I want to notice here, so this is a classic thing to do on power supply. So right now, I got 1 volt going into this thing. All right. Now Musa can see that at least, right? All right, that's 0.3. It's handy that you're close by, right? So it's 0.3 amps going into this thing. So how can I make the motor apply more torque? Well, and how do I make more current go in? Nature is just saying that's how much current needs to go in there right now. Well, I can decrease the voltage. All right. Well, let's say if I want to simulate more mechanical torque, I can grab the shaft. Right. So that's gonna, if I grab the shaft, in this case, I can grab it pretty hard. I see he's now pulling an amp. Right. He's trying hard. If you felt my fingers, you would feel him trying to slip underneath my fingers. I let it go and it goes down to 0.2. Now, if I increase the voltage on this guy, again, let's let him scream a little bit. All right, that's about 3.3. Now, if I grab the shaft, I can feel it burning up on me. It's getting my fingers hot when I do that. But I see it going up over about 3 amps or so, right? Why? Because I am basically saying, hey, I need more torque. I'm putting more mechanical load on this, just like if I had a pump, right? If I had a pump that I had to turn, it's got to push against the fluid. In this case, it's got to push against the friction of my fingers, right? And so it's increasing the current that it's putting out to try to produce that torque. All right. This guy does not sound like he's in good shape. All right. But that's an important concept. So if I'm talking about designing a motor drive, right? So if you guys are doing a robot or something like that, you need to kind of figure out, well, how much torque am I going to have to produce? Based on that amount of torque, I need such and such an amount of current. And that tells me how I design ultimately the power supply that provides this thing. Because the power supply, yes, it gives voltage, but it also gives amps, right? So I need to think about sort of the ampacity or the amperage that this thing's gonna provide. All right. Bottom line to this is I think about the torque. I'll say the torque electrical that the machine produces is K times IA, some constant. And you'll see if you look at a DC motor data sheet that it has a constant, a motor constant. And that motor constant is K. All right. So in this case, sometimes I say, if I look at this guy carefully, I guess maybe I shouldn't use the G right off the bat. One other way that we sometimes write this is G times IF IA. So if I do have a separately excited machine, and I should be, let me call this G1 here, just to differentiate from the fact that there's some different constants in there. All right. Basically, this guy could be GIF IA, where this is equal to K, the constant. This, I only need this whole G thing if I have basically a field winding that I'm using. This guy here does not have that field winding. Okay, so it doesn't matter. All right. So that's how I think about the torque that this machine produces. Now, the other thing that's important is ultimately I got to figure out something about the speed of the machine, right? Because you saw what was kind of happening. You heard a louder noise as I increased the voltage on that thing, right? Why was I hearing a louder noise? What's that? Higher RPM, more voltage, more speed, more current, more torque. All right, that's the key relationship, right? So more voltage, more speed. Now let's see if we can figure out why that should be the case. So how could I figure out whether that's the case? I guess I could do some Faraday's law stuff, but I could also say, all right, if I think about the machine, if it's lossless, and no real machine is lossless, I have the electrical input, I have the mechanical output, right? And maybe I have another input here to create the field, all right? But this guy is not doing work. He's just creating field for me, okay? So from this perspective, what's the input power and what's the output power? If it's lossless, I know that P in equals P out, right? What's P in this case? VA times IA, VA times IA. So VA was the voltage source here. IA was the current that was going into it, all right? VA IA equals P out. How do I write that? Torque times omega, torque times speed. And I'll write that as omega M, I guess, because that's my mechanical speed. So what else do I know? Well, I've figured out this torque is equal to K times IA. So that means that VA equals IA equals K IA times omega M. And I got some stuff that cancels there, right? IA's cancel, and I see that VA equals K times omega M. All right, now, that says that the voltage at the terminals is proportional to the speed. We've seen this story before. We saw the same thing in the synchronous machine, right? What's happening is I have created a magnetic field. I got windings moving in a magnetic field. They're inducing a voltage in those windings, right? It's Faraday's law at work, right? This is a lossless machine, right? So I should be able to see this. This says that if I spin the motor at a frequency omega M, that I'll see a voltage VA. So I'm going to take this same motor and try to do that. And so I'm going to get my trusty turbine, which is my drill, right? And stick this guy on here. And let's see. So I go over here and switch again. Now this is a DC motor, so I want to measure the voltage on it. So what setting should I put this guy onto if it's a DC motor? DC, yeah. All right. Good answer. So now what I'm going to do is I'm going to hook up my terminals here to the multimeter. All right, and so he's not spinning. Omega M is 0. So hey, guess what? The voltage there is 0. That's good, right? If I start to spin this guy, now what I see, I get voltage, right? So I'll spin it as fast as I can. I'll squeeze the trigger all the way down. And that got to what, like 0.64 or something like that. I spin it kind of slow, 0.04, spin it faster, right? I get more voltage, right? Voltage is proportional to speed. All right, so that's the basic idea of a generator at work right there. All right, so
you use a DC machine and the DC generator.
Yeah, I can make a DC generator. And you don't see that as much anymore, but we can go into some stuff like subway systems and things like that. Sometimes use that for different purposes. But yeah, I can have a DC generator for sure. All right. So in this case, what I end up with by the time all is said and done is I end up with, I said, this is if the machine is lossless. It says that if the machine is lossless, the terminals, I was at the A terminals when I just made that measurement, right? So VA was what I was measuring. Says that inside this thing, there is again a proportional source, K omega M. There's a dependent source. Any of these machines, there's dependent sources, speed dependent sources. Now I said it was lossless, right? Is a real machine lossless? No, it's not. There's going to be some resistance to it. So it's going to have that. Now, in addition to resistance, it also has inductance. But we should know that by now. This is LA and RA, where the A stands for armature. Now, for the most part, when I examine DC machines, I usually consider L sub A to be 0. All right. When I'm analyzing a crappy machine like this, his resistance is high and its inductance is pretty small. I'm going to talk a little bit later about why I consider the inductance to be so small that it's negligible. Basically, the time constant of this electrical system is usually a lot smaller than the time constant of the mechanical system. In other words, the thing that's hard about spinning up a motor is not getting the energy into the inductor. It's getting the energy into the rotating mass. All right, that's the thing that takes more time. All right, I don't want to get into all those weeds, but this is our basic circuit. Coupling this with the fact that the torque is equal to K times IA. And if I have a field winding, it would be G times IF times IA. All right, now there is a whole kind of like Forrest Gump scene sort of list of DC motors where it's like there's all kinds of motors, right? There's a series motor, a shunt motor. Basically, there's all kinds of different ways that you can connect the field winding to the armature. So I can, in other words, I can put them in series with, I could have a voltage source and I could hook IF and IA up to each other. Or I could connect them in parallel with each other, or I could excite them separately, or I could do a combination of them, right? So there's all sorts of different ways that I can connect them. We're not going to get into all that stuff. In other words, there's a series motor, a shunt motor, compound motor, basically relates to whether IF and IA are in series with each other, parallel with each other, or just completely separate, okay? Problem 4 on the homework, they're completely separate, and I have a separate IF. All right, and we're gonna look at a demonstration of that on Wednesday, okay? All right. So let's real quick, we got about 5 minutes. Let's do a little bit of an example on this guy here, which is pretty similar to what I have in the homework, okay? So if I talk about the way this guy is going to behave, let's say like in the homework, I give you an example and I say, in that particular case, I took a motor and it was operating at 400 RPM. And I measured a voltage at the output, an open circuit voltage that was 2.7227 volts, right? So what I want to do from that is I want to figure out what is the K value, right? What is K? So how do I figure that out? So I know so in other words, it was running as a generator, just like I had right now, somehow something like the drill, spinning it up, okay? When speed was measured to be 400 RPM, and it's easy to get a speed sensor. Anytime a control system has a speed sensor of some sort, right? When this guy was at 400 RPM, the open circuit voltage was this 2.7227 volts. All right. So how would I figure out the K value? Right. So let's look at this picture. Yeah. How much current? So IA, in this case, usually we consider him as a motor. So when it's a motor, IA is going in. Right. If it's a generator, IA would be going out. Okay. He's operating like this. How much current do I have if he's open circuit? Operating as a generator, open circuit, IA is 0. So if IA is 0, VA and this voltage better be the same, okay? So in this condition, all right, I have VOC is here. Bless you. This guy is K omega M. But there's no voltage drop across here, right? This voltage is 0 if there's no current, right? So in this particular case, I have the VOC equals K omega M. So K would be VOC divided by omega M. Now, if I'm doing this in my typical kind of SI units, what should I do with the omega M? I gave it to you in RPM because that's the way we talk about stuff, but I got to convert it to what? Radians per second, right? So if I converted that to radians per second, all right, that works out to be omega M is 400 RPM revolutions per minute, or 41.8879 rads per second, okay? And that gives me a K value in this particular case of 0.065. And the units on this guy would be volts seconds per radian. All right, now this is actually for a real machine. I mean, they all should be for real machines, but I took this from a machine that I used to use when I taught control systems. Right, so it's I used to make the students figure out all the parameters on this particular machine. All right, so 0.065 volt seconds per radian is the K value. Now, the next thing I did was I said, okay, well, I hooked this thing up into a circuit and I used it to do something. So I had basically a 10 volt source. So I got 10 volts hooked up to the machine. And I measured this condition right here. So here's RA like that. Yeah, and I'm assuming here, I'm assuming LA is approximately 0. In this particular case, my RA is actually 13.4134 ohms. Okay. And I'm going to say that this guy is operating, and the torque that I measured, the torque that it was producing, or let me explicitly say that the current that was measured was 281.855 milliamps. Okay. Right. So a couple of things I want to figure out. It's really pretty straightforward to do these problems because they're not even, I mean, they're DC. They're not, so this is circuits 1 analysis to really do this, right? Question that I asked there in the homework, what's the torque that this machine is making? So it's hooked up to a load. I got 10 volts hooked up to it. What's the torque that it's making? K times IA. All right. So whatever load it's operating against is requiring K times IA. So the torque that it's making is K times IA. So it works out to be 0.065 times 281.855 milliamps. That works out to be 0.0183 Newton meters. Okay. Let's say I want to figure out what speed he's operating at. How would I figure that out? KVL, right? Figure out basically, so 10 equals IARA plus K omega M. I know IA, I know RA, I can figure out omega M. Okay. What would happen if I tried to make the machine produce more torque? In other words, if I grabbed the shaft here, IA would increase. All right, IA would increase. What would that ultimately then do? So IA would go up. What's the speed would go down? How do I know that? Well, math. Yeah, J d omega M by dt equals tau electrical minus tau mechanical. If I grab the shaft, torque electrical is going to go up, right? And the speed is going to adjust itself so that the torque produced is going to exactly balance the torque that's needed to spin the load, right? So the thing's going to slow down and the torque is going to go up. All right, we're going to look at that more carefully on Wednesday, right? We'll look at that in some more detail. But this is the basic premise. Now here's a question. If I make this thing produce more torque, so if I grab the shaft, it slowed down. Let's say I wasn't happy about that. Let's say I wanted to make a constant speed motor. What would I have to do to make the motor speed up? Put more voltage on them, right? So if I increase the voltage, so if this went from 10 volts to say 12 volts, omega M would increase, okay? How would I do that though? That means that this voltage source needs to be variable. I need feedback because I would need to sense that the speed changes, and on the basis of my measurement of the speed change, I'd have to increase this voltage. What's a good way to make a voltage source that can increase itself and decrease itself? Potentiometer is the simplest way to think of it, right? But it's a really inefficient way to do it because I have to basically burn up power in a resistor. So the best way to do it really is to make use of transistors and use some power electronics. All right, so what we're going to do is we're going to talk a little bit about the basic concepts of power electronics. And we're going to start that on Wednesday. Basically, how would I create a voltage source that would drive this thing? Very simple idea. All right, and we'll kind of introduce it on Wednesday. All right, that's it. Again, if you guys have questions.